Good afternoon, and welcome to the 2023 annual event of the American Teilhard Association. It is good to see so many of our members and guests gathered today. You're so very welcome. So a few reminders and an overview of our schedule. We have a wonderful program prepared for you today. A chance for all of us not only to learn firsthand more about the images captured by our new telescope, but also to contemplate the beauty of these images. Someone has once said that seeing is a matter of placing oneself at the right point of view, of moving in close with a microscope or distancing oneself with a telescope. Today, we have a rare chance to look through the telescope, to see back through the eons of time, to ponder the wonders of creation, and to plunge ever more deeply into the mystery, who is our God. We'll begin with a short poem read by our board member, Kathleen Degnan, and then I will ask our presenters to introduce themselves. During the first segment, Libby Osgood will engage Richard D'Souza in conversation about his work at the Vatican Observatory. This segment will be followed by a short break. And then Libby will again engage our astronomers, this time Guy Consolmagno, in conversation about his work, which is quite different from Richard's. And he also is at the Vatican Observatory. And then finally, Andrew Del Rossi will gather questions that we ask you to accumulate during the talk. So if you have a question or have a comment, please put it in the chat. So when it's time for questions, Andrew will be able to find your question and ask it if possible. And then we hope to end with a musical triptych newly composed and performed for this occasion to honor the wisdom of Pierre Teilhard de Chardin. So just a reminder before we begin, please be sure to mute your speaker throughout the event unless you are called on to read or to speak. That will really help the sound, I think. So I hope you enjoy what we have planned for you. For those of you who are not yet members of the American Teilhard Association, please join us, and you'll be able to find our web address in the chat, if not now, shortly. So to prepare our hearts and our minds for what we will be experiencing, we begin with a short poem. So Kathleen Degnan, would you please unmute yourself and read for us the poem by Rebecca Wilson. Thank you.
Let there always be light. Searching for Dark Matter by Rebecca Elson. Let there always be light. Searching for Dark Matter by Rebecca Elson. For this we go out dark nights, searching for the dimmest stars, for signs of things unseen, to weigh us down, to stop the universe from rushing on and on into its own beyond, till it exhausts itself and lies down cold, its last star out. Whatever they turn out to be, let there be swarms of them, enough for immortality. Always a star where we can warm ourselves. Let there be enough to bring it back from its own edges, to bring us all so close, we ignite the bright spark of resurrection.
Thank you, Kathleen. Such a lovely rendition of that poem. And now, Libby, please introduce yourself and your guest to tell us about yourselves.
Thank you, Kathy. My name is Libby Osgood. I am a sister with the Congregation of Notre Dame, and my background is aerospace engineering. I worked on a few NASA satellites with Orbital Sciences, and more recently, Kathleen and I published a book called Teilhard de Chardin, A Book of Hours. And so I bring this up to a room of Teilhardians so that if you enjoy praying with Teilhard, it's a book of his words, just reorganized in a really beautiful way through evolution, so that we can pray with Teilhard through the earth. And maybe I'll keep this going and ask Brother Guy, would you like to introduce yourself?
Sure, be happy to. I'm Brother Guy Consolmagno, and I'm a planetary astronomer. I come from Detroit originally, so don't let the long Italian name scare you. My background was I was educated at MIT for my bachelor's and master's, the University of Arizona for my doctorate, and had many adventures between getting the doctorate and finally entering the Jesuit order 30 years ago, 1989. In 1993, exactly 30 years ago, I was appointed to the Vatican Observatory. And 7 years ago, Pope Francis made me the director of the Vatican Observatory. But through that time, I've continued my research into meteorites and asteroids, small solar system bodies, and the origin of the solar system.
That's wonderful. Thank you so much, Brother Guy. And Father Richard, would you like to introduce yourself?
Sure. Thank you, Libby. I am Father Richard D'Souza, originally from Goa in India. I'm a new addition to the Vatican Observatory, having joined its staff 4 years ago. I'm presently based in Castel Gandolfo in Rome. As part of my journey, most of my education has been between India and Germany, where I did most of my formal technical education, including my doctorate. I spent a few years in Heidelberg and Munich before moving to Ann Arbor in Michigan for a postdoctorate and then returning here to Castel Gandolfo in 2019. I basically work on the formation and evolution of galaxies. I think of these large objects in space, very far away from our solar system. And yeah, I'm pretty much here taking care of the community here in Castel Gandolfo as part of my other spiritual duties.
That's wonderful. Thank you both so much for being here. And I think we'll move into a conversation now with looking at the JWST and what from a Teilhardian perspective. So for everybody on the call, I'm sure you're aware of Pierre Teilhard de Chardin, but in case you're not, he lived in the first half of the 20th century. He was a stretcher bearer in World War I. He wrote prolifically about spirituality, his travels, his scientific research in geology and archaeology. And he had a tremendously bold vision for the future, so much so that he created so many words to describe his ideas that people often find his work daunting. As a Jesuit priest, he was obedient to the request of his superiors. And so even though he wrote prolifically, his ideas, he was asked not to publish his ideas. So he didn't, he obeyed. And it was only in the decades following his death on Easter 1955 that his writings began to come out. So I think each one of us on the call might summarize his life differently or highlight different elements. But as an engineer and religious sister, these are the things that I find most interesting. And one I left out that I love is there was a fossil named after him from his days of wandering the desert in Egypt while he was teaching as a young Jesuit. He wandered the desert so much that there was a fossil that he found, and they named it after him. So I think the thing that's most interesting to me is how he could reconcile faith and science and help to develop the cohesiveness and truly integral connectedness between them. And Guy and Richard, you are no strangers to this concept, I'm sure, being asked about this all the time. So the title of this event is based on Teilhard's quote, "Seeing. We might say that the whole of life lies in that verb." And he continues, "The history of the living world can be summarized as the elaboration of ever more perfect eyes, with a cosmos in which there is always something more to be seen." That's from The Phenomenon of Man. So Richard, I understand that JWST has developed more perfect eyes, you might say, to see the cosmos. So my first question is, what does it mean that JWST is a near infrared telescope? And what are some technical tidbits that help the JWST instruments to see?
Let me start off with just trying to describe how JWST can see what we normally cannot see. Many of you will know that JWST is an instrument which is really new, different from the instruments we have had before, especially in space. It's an infrared telescope. And what it means is that basically it looks at wavelengths which are much longer than the visible wavelengths, the wavelengths which we are normally used to. These are very close to the infrared, so beyond the red. So JWST was constructed basically to answer two very basic questions. And one of them was, first of all, to look at the first galaxies that were formed in our universe, to see them. One of the things which we notice when we look up at the night sky, we notice that it's dark. This is called the famous Olbers paradox. Why is the sky dark? If the sky is filled with so many objects, if there are so many millions and billions of galaxies, and every point you should see some source of light. And the resolution to Olbers paradox is that when you begin to look at things which are very, very far away, their light slightly changes. And to introduce that, if you look at this plot, which I'm putting up ahead of you, we think that our universe is about 13.7 billion years ago. And our galaxy, which we know, was practically formed around after the first billion years. And our sun, about 4.5 billion years after the beginning of that galaxy. So about about 7 or 8 billion years would be the approximate age of the birth of our sun. But what we really want to understand is how these large galaxies, which are basically made up of billions and billions of stars, what were their origins? What were their basic origins? So our aim is to look really back into time and to look at these earliest galaxies very close to the Big Bang. And our problem is we cannot see those galaxies, and we call them the dark ages. And to say we cannot see them, partly because they are very faint, but the other reason which we can't see them is that the light which they shine changes as it travels to us. And it changes in such a way that it gets shifted from the visible to the infrared. And this change is due to what is called as the expansion of the universe. We think the universe expands, the universe is expanding, and due to the expansion of the universe, everything what was invisible now becomes infrared. So without an infrared telescope, you really cannot look at these first galaxies. So the basic reason why JWST was, one of the reasons why JWST was created was to look beyond the visible and to look beyond the galaxies which you can see to the very first galaxies. And the only way you can do that is in the infrared. But there is another reason why we would like to also look to the infrared. And that is that many objects in space, stars, especially stars, create what is called as dust. Now this dust blocks the light. And therefore, what we can see is when we see stars being born, they create a lot of dust. You see here on the right is a picture of the Carina Nebula, a very beautiful object in the visible light.
And that dust blocks us from seeing what is going on within the nebula. However, if we are able to look at a longer wavelength, like infrared, whose dimensions do not actually correspond to the dimensions of the dust, we can be able to see through that dust. And that's the image on the right, which you see of the same nebula now, but the stars shining through, especially the young stars that are being born at the center of that nebula. So there are two reasons why we really need a James Webb Infrared Telescope: to see further, because light gets red shifted, becomes infrared, and to peer through dust. Now, to do that, we look at the infrared spectrum. So, as I mentioned earlier, what we are quite sensitive to is the visible light, and that's what Hubble Space Telescope was really good at, taking those brilliant images in the visible light. The James Webb Space Telescope, which is recently launched, is a bit different from Hubble. It can see a bit in the near infrared and the infrared. The near infrared will be very close to the visible. The infrared is just beyond the near infrared. So, and in past, we also had another infrared telescope called the Spitzer Space Telescope, which we can call as the predecessor of Hubble, of the James Webb. What do we need? So if you look at the Webb telescope, it has a couple of instruments which are designed for various parts of light. So a bit of the visible can be seen through an instrument called NIRSpec. It's a near infrared spectrograph. Basically, it can look at different wavelengths and get a spectrum. Similarly, there is an instrument called NIRISS. But perhaps the biggest and the most important instrument is NIRCam. It's actually the camera which can look at the infrared and create all those brilliant images. So the majority of the images that you're actually seeing, which you will be seeing, are from NIRCam. And then there is a unique ability, an instrument which can look in what is called as the mid-infrared, so longer wavelengths, and that's called MIRI. It has a couple of bunch of 4 instruments with which it's capable to look in the near infrared and the mid-infrared. Now, how does James Webb do this? Most of us would know that an object, all of us emit radiation. And we emit radiation in various frequencies. Most of you will also have seen or have heard of how the military often uses infrared glasses to look at night, to look at objects which are giving out some radiation. So everything is giving out radiation. If a telescope like the James Webb really wants to look at all this near infrared radiation, it must first go very far away from the sun and the earth and the moon to a point where it will not be disturbed, but it also needs to be very cool, very cold, because you don't want the light, the heat from the telescope and the instruments of the telescope to interfere with the observation. So you basically have to cool the telescope to a very low temperature, about 230 degrees Celsius, which is about minus 388 Fahrenheit. And the way it does that is by putting up a big shield which protects us from the sun and is able to reduce the temperature of the instrument. So you need a cold infrared telescope to be able to see, a real cold telescope. Most people will try and compare James Webb Space Telescope with the Hubble telescope. Just to give you a sense of those dimensions. The Hubble telescope is about 2.4 meters in diameter. On the other hand, the James Webb Space Telescope is 6.5 meters in diameter. The increase in diameter is due to 2 reasons. First of all, you want a larger collecting bucket of light. So the bigger the bucket, the more light you collect. But also, if you want to really look at the sharpness of the image all of us have been used to these very sharp images from James Webb. The sharpness of the image, the resolution power really depends on the diameter of the telescope. So the equivalent to reproduce the equivalent resolving power in Hubble, you need a much larger mirror because it's of the wavelengths are slightly different. The wavelengths are longer. And there are also other factors that gold is it's made up of, it's gold coated. And gold coated is because it's also the best material to reflect the infrared light, which comes from these distant objects. So just to give you a sense of what Hubble did and what Webb can do. What I'm putting up before you now is on the left is one of the deepest images made by Hubble, the Hubble Space Telescope. This image took 11 days to take. That means the camera was exposing itself and collecting light for nearly 11 days. The same image, more or less the same image, when it was redone by the James Webb Space Telescope, just because it's a larger bucket, you could do it in less than a day. That's the power of using a larger bucket, of a bigger mirror of light. And the resolution is very comparable. So you can see that the resolution on the left, the sharpness of the images is equivalent to the sharpness in the Webb. So the Webb telescope is really performing very well. It's producing some very spectacular, really, images. And it's being able to do this because the brilliant work of space engineers who constructed these instruments. It was long in the making, but it's also because it has a larger mirror and is able to look things in the infrared.
Wow, thank you for that. That description of where the sensors are and how each is measuring specifically. I think one of the things that fascinates me most about the JWST is, as you say, most of the images are coming from the near cam.
Yes.
But because or that we would see, I should say, that we would see on Google.
Yeah.
But can you comment on the coloration of it? Because if we're in the infrared range, please go ahead.
Yeah. So I kind of skipped that and I wanted to bring it up a bit later, but that's a good time and a good way of bringing it up. So as we realize that these two images are made up, it's a colored image. Okay, both are color images. And both Hubble and Webb, to make these color images, actually observes in various frequencies. So what we do is that we would take a filter before that camera and we would expose this image using various filters. So what the camera just gives us is a black and white image, which is then reconstructed together to give you a color image. And you kind of assign the colors manually, as by hand, by an artist who will actually assign those images, those colors. So what the Hubble, it becomes easy to assign the colors because these frequencies correspond to the frequencies which we are used to, which our eyes are sensitive to. The frequencies in which James Webb, the wavelength in which James Webb observes, on the other hand, is something beyond what the eye can see. So then it depends really on using one of the scientists at the Space Telescope Institute, which creates these images, would then try and transpose these infrared filters into a corresponding set in the visible wavelength for us to see. And that really helps us to imagine or to visualize, because that's the best way we can actually understand something, these images. So basically they are false colors or transposed colors would be the best accurate description of that, maybe.
Well, and that's so neat because it makes me think of when we're looking at pictures on Instagram or Facebook or on our phones, you can use different filters to make the colors more brilliant or to make it black and white or to give it an old time feel. And often when we look at an image, especially coming from a telescope, you imagine that it's precise and perfect and truth, whatever that means,
Yes.
right?
Yes.
So it's neat to understand that it is filtered and it's recreated and imagined in some and not imagined, but altered
Yes.
from the original image.
Yeah, it is altered, but let's sort of say the artists or the scientists who actually assigned these colors assigned the colors to convey information in such a sense that the blue colors are assigned to things which are in shorter wavelengths, so corresponding, and the red colors are to the longer wavelengths. And in a sense, if you know the filters used in the corresponding image, and I will indicate them as we go on, you can actually understand what particular material is actually emitting that light. And based on that, you can actually understand the physical processes going on. Is it a star being born? Is it dust emitting light? So the colors are, in a sense, transposed and not corresponding to what we are sensitive in the eye, but are used to convey some sort of physical meaning. And I'll try and explain that as we go along.
Oh, wonderful. Thank you. One of the things that you've said before is, and I quote you here to yourself, is that your work is to understand how nature works. The more you discover about nature, the more you're able to give praise to God who created the world in this wonderful and complicated way. And as I mentioned before, the complexity of the universe is something that Teilhard was interested in as well. He said, in this darkness, as vast, rich, troubled, and complex as the past and present of our universe, we are not inert. We react because we undergo. And he said that in the divine milieu. And by that, I think he means that we react as in everything in the universe is constantly in a state of reacting with everything around it. And of course, I'm not the first to think that, but in a great ongoing relationship and truly an interconnectedness. So my next question for you is, and it's to do with your next topic here, what is the JWST doing to help us learn more about the distant universe? Or as Teilhard might describe it, what can the JWST tell us about the interconnectedness and reactiveness?
Well, thank you for that question, Libby. So one of the, I always like to initiate by saying there are three basic questions in astronomy. One is, where do we come from? Where are we going? And are we alone in the universe? And where we come from is that fundamental question which JWST is trying to answer at the very beginning of the universe. So I need to be a bit technical here to try and transcribe the way astronomers talk to the way we will understand. So one of the things which astronomers try to do to try to understand the distant universe is they try to talk about time in terms of this red shifting of light. So what we would, if you look at this little plot over here, it shows you what we would call as look back time on the right axis, on the vertical axis, which is basically time, how long did that light take to reach us? And here we are talking of giga years, billions of years, right? So so we're talking about 2, 4, 6, and the age of the universe would be 13.7 or 13.8 billion years. This is that light from here would take 13.8 billion years to reach us. And on the x-axis, on the other hand, is the equivalent way in which that light would be shifted along the spectrum, which we would call as redshift. So basically, if you are looking at the very early universe, you are talking about galaxies which are redshifted beyond 6, much beyond 10, and probably approaching very much, to 12 and 13. So our aim of the James Webb Space Telescope, so prior to James Webb, we could see galaxies up to redshift of 10, which is pretty much, very close to the start of the universe, a few million years, 100 million years out of the universe. But we're really interested in that very short segment of time before, beyond what Hubble could show us, is to understand when the galaxies were actually growing from their little seeds into becoming those monstrous objects that they are today. And we expect from our theories that this growth happened in this very short segment of time. And if we can catch that growth in action,
then we can understand, oh, that's how our galaxies were formed. That's where we come from. So the game is really to look at these redshifts beyond the redshift of 7. So very early in the universe. So the first images one of these James Webb did was to look at the distant universe, but it needed also to understand this distant universe and to make sense of the answers that would come out from these images. What it would mean was that what you want to do in science would be to first do an experiment, but make sure that it corresponds to what you already know, and to make sure that these answers make sense. They are consistent with each other. So one of the first things James Webb did is to look at a massive cluster of galaxies. These are monstrous objects. Okay, these contain about 100 to 200 large galaxies which are clumped together, and they're called a cluster. And these clusters are very at a distance of about, at a redshift about, let's say 7 billion years away, so about redshift about 6. And they help us to look further because they act as a gravitational lens. They actually help you to see things much further back because light bends around these massive objects and come to us. So using a galaxy cluster, you can actually make sure that the answers you get are consistent. That was one of the first. So the first image that James Webb took is an image of a galaxy cluster, which I will show you now. And this is the cluster. It's cluster SMAC 0723, made with the near camera in many filters, and then put together in this kind of false coloring system. And first thing you will notice is that you will see this, the images is spectacular. You can see a very bright star right in the bang of the center, which has a very sharp, a strange spike pattern, which is fixed, but that's the way because the mirrors of James Webb. You will see galaxies which look like galaxies, which are like fuzzy objects, and you will see galaxies which will be stretched, which are likely stretched in curves, and these curves go around. And what this is that basically these are lensed galaxies. So the quick way of understanding this image is that everything which is nice and round is about 6 billion years ago, and everything which is nice and curved in these nice curved images is very distant away, and they are lensed and made bigger by this galactic natural lens of the galaxy. Oftentimes, you would have multiple images with the galactic cluster. That means two curves would correspond to the same galaxy. The same galaxy would appear a number of times. So you can double check your answer if you think you got it wrong. So, scientists want to make sure that they get everything right the first time before actually launching into crazy theories about the beginning of the universe. One thing you notice is that the immense detail in this image. It's true that we are actually looking into a galactic cluster. There are thousands of galaxies, but you can actually see all these small little details. And what the scientists are really looking for are not these big objects in the center, but these tiny dots, which you will see in the image, because those are the most distant galaxies that you can, which we expect to find. So the first thing they did was they looked for these galaxies. And this image is actually known to us from Hubble. So we knew where to look. So they identified a number of these very small, tiny dots. And you can see these images blown up over here. So let's start with the one on the top, which is over here. It's about 11.3 billion years ago. That's light reaching us. And you can see we measured it by taking a spectrum. And that galaxy is producing stars and is giving off hydrogen lines by this long production of stars. So we can very much identify, by looking at the spectrum, you know what redshift it is. And we had a understanding that these were very distant galaxies. So immediately the scientists took the image and took a spectrum at these particular points, which they were expecting. And what they found was that you could do this spectrum in less than a few hours. Previously, we would take about 10 days to do it on the ground from using large 8-meter class telescopes in Hawaii. And here you could do it very fast on the ground. And we immediately identified these very distant early galaxies. So the first is at 11. The second one is at 12.6 billion years ago. And you can see already that its spectrum is slightly shifted to the right. It's been red shifted. The third is at 13. And the last, which is shown here, is 13.1 billion years ago. That's like a few 100 million years after the Big Bang. So this immediately confirmed in some ways that the telescope was working very well and was giving us some very excellent results. Let me zoom in on the last object. The spectrum, first of all, I want you to realize is that what the scientists, we will be excited at this image, but what the scientists are excited about are the dots. So that's what we are excited about, because the dots are the really earliest things. And the dots, if you zoom them in, just look like a small little blob. But from that blob, and if you take a spectrum with one of the other instruments, like here, which was done with near spec instrument, you can actually see all these beautiful lines coming from this very complex object, which is hot and producing large amount of stars. And basically from all these lines, these emission lines from the spectrum, you can try and understand what is actually going on in that spectrum, in that galaxy. How many stars it's producing, how big it is. Okay. And this is really exciting because we've been able to do this before, but it would take us days to get it done. And now we can do that like in an industrial scale. It's like immediately, within hours, get the spectrum done. The other thing which you can easily see is I told you that sometimes an image, to double check, a single galaxy would have a double image. And this is what I could try to demonstrate you to see, okay, let me put a spectrum on these two kind of stretched galaxies. And we know that they come from the same galaxy. Do we get the same spectrum? That's a double check. And that's what they did. And they checked it out and they correspond to the same galaxy. So we have a double check that our instrument is working very well, but it's also being able to go very distant in the universe. Now let's go quickly to the more exciting parts of this image. Now, similarly, now you can point this telescope now into the distant space, not at a galaxy cluster, and then you can redo this experiment, but now just looking for those very distant galaxies. And immediately they found all these little dots of galaxies, which appear to be very different. And you can always see here that in this image, first of all, it's filled with dots. There are galaxies everywhere you look. It's made in 3 filters, and the 3 filters have been assigned the colors red, green, and blue for the various frequencies which has been assigned. And already in this image, we have been able to identify and confirm these 4 galaxies, which are very distant. And you can already see that the redshift is now creeping a bit higher, 13.2. In the previous one, we had 13.1. This is now 13.2. And the idea is now, let's look at all these dots and try and identify which are the earliest galaxies. Can we get to redshift of 15? Can we get redshift of 14? Now, how do you do this in this large image? Let me just go back and give you an example of what scientists do. So the first thing that scientists do is that they take a spectrum of a galaxy, okay, and they'll observe it in various filters. So what you are seeing now here is a spectrum of a galaxy which is observed in various filters with the old telescope, with Hubble, in the visible light. So we are observing 606 would be just bang in the middle of the range which we can see, 606 nanometers. And what you can see, this galaxy is the filters and the images correspond to the galaxy. And if I get to play this image and the galaxy is being pushed into further and further away, you can see that the galaxy would appear in certain filters and disappear in other filters. So instead of, let me play that again for you to see. It's available, and slowly as it becomes a higher redshift, they disappear from certain filters. This is called as the dropout technique to find galaxies. So if you have a large image and you don't know where to point your spectrograph to get a spectrum, you would take these images, use these filters, and try and then identify your source. It's a very approximative way of trying to identify your very distant sources. So that's what Hubble did. That's what James Webb Hubble did in the past. And now James Webb is doing in the near infrared to get you even further in redshift. So the first one which they found very easily, and this is a confirmed case, and I hope you can see that the galaxy is barely visible. There's a galaxy at the center of this image, barely visible, and gets visible in the 200, the 277, the 335 filters, 356 and beyond, but is not visible in the first two filters. And this galaxy now is at a redshift of 12.63. Okay, this was a confirmed case. And what we have even been able to do is get a spectrum. And we have confirmed that this guy is one of the first galaxies found, which is using this method of dropout technique. But then this created a bit of control. So these have been confirmed, as you see. We've been confirmed their cases, they've confirmed their spectrums. And we know that these galaxies are sure galaxies at very distant universe. But there arose immediately a problem. People using this technique found galaxies at redshift 14, 15, galaxy candidate at 14, 15, 16. But according to our theories, those galaxies should not be there. There's not enough time for these galaxies to grow to those large dimensions. So these galaxies are pretty okay. They are pretty small, which I'm showing you in this image. They're confirmed. They're pretty good. But there have been about 25 odd papers being published telling us that we have found too many young galaxies, big ones, at redshifts of 14 and 15, which shouldn't be there. And our full theory of how the universe would be 13.78 billion years old, how could these galaxies be so massive within a few 100 million years? There's no physical way that this could be happening. Furthermore, a paper was recently published 2 months ago, in which a certain group of researchers found, using the same technique of this dropout technique, a number of massive galaxies at lower redshift. So the galaxies would grow over time. And even at redshifts about 9 and 10, you expect them to be of a certain size, but not too big because you need time to grow. But these galaxies, which these people found, Labbe et al., it was published in Nature and has created such a big craze, has shown us that the galaxies are much more than what they are. Let me try and explain this plot to you. This is a plot of, I'll just use one of on the left-hand side. So what you have here on the left-hand side, on the x-axis, is the mass of the galaxy. So 10 raised to 8, so 10 raised to 9 would be about 1 billion solar masses. 10 raised to 10 would be 10 billion solar masses. 10 raised to 11 would be that. So at a redshift of about 9, let's say a redshift of about 9, you should expect the number of galaxies should be this line which is in gray, the lowest line, because that's the line you should expect. If everything is able to convert to stars like very efficient machine, then you would reach an efficiency of 0.3 and you would find maybe a little bit bigger galaxy. But if the efficiency was just impossible, because nothing is so efficient in the universe, which create stars would be like 1, and any good physicist will tell you, you cannot create a machine with efficiency 1. You would have the galaxies which are right here in this black line. And the idea which came about with the discovery of Labbe, or this claimed discovery of Labbe, would be that the size of those galaxies, the number of them which they found, would put it really at and an efficiency of 1. And we know that this cannot be true. We know this. So something is wrong in our theory. And this is creating such a big buzz in the community. People are fighting, throwing coffee at each other, tearing up papers, shouting at conferences, just because right now, if this is true, it's yet to be confirmed because we can take a spectrum. We haven't taken a spectrum of these galaxies. But if this is true, we astronomers would be tearing up our cosmology textbooks and rewriting them because we just didn't understand anything. And this has been able because we just been able to see things which we've never been able to see before.
Well, and that's so interesting because that wouldn't be the first time that astronomers would have to do that, right? As we learn more.
I hope not, but yes, if you're forced to, I will.
Yeah. That's so neat that it's evolving so much. I mean, it sounds like these tools and instruments that we've used over the years are not only evolving in their capability, but helping us to understand more and to understand what we may or may not understand. And that makes me think of one of Teilhard's quotes: "We must test every barrier, try every path, plumb every abyss," which advocates pushing towards constantly working, constantly understanding further. So in just the last couple minutes we have left, I'm before the break, are there other deep questions about closer galaxies that we're hoping JWST will answer for us?
Yes. So one of the great things about JW's Web is it helps us to peer through the dust. And so these are galaxies much closer by. And one of the other big questions in my field in the formation of galaxies is, why do galaxies not produce as many stars as they should? Why is the efficiency, which we know from galaxies close by to Earth, why is it so low? And part of that process is to actually look. So if I'm just going to skip this, okay, just give me a minute. My slides are very slow today. Is to look at nebulas of galaxies. So parts of galaxies which are producing large amounts of stars. So this is the Carina Nebula. It's quite close to us. It's a couple of the hundreds of few light years away within our own galaxy, and it's a nursery of stars. Okay, and this is an image from the Hubble Space Telescope. But the Hubble Space Telescope would not have, and what we are seeing here is that these stars are being born in these nurseries, but also being bound in these shreds of dust and gas, clouds of dust and gas. And we haven't been able to peer through those clouds of dust and gas. And now James Webb has given us that magical ability to look at the same image. Now this is in NearCam, but to peer through those clouds of dust, to actually peer through it. So what you actually see here is you see these very bright, let me try and explain this a minute. You see these very bright stars on the top of the end of the image. These are very massive stars. And these massive stars are shooting out radiation and winds, and are actually pushing the dust and the gas and giving it those very, very, how would I say, very concise and defined borders, which you see in this image. This is actually because the massive stars are pushing the gas. They're pushing the gas and making it more compact. But if you think of making it more, what's happening is by making it more compact, you're increasing the density of gas. And what increasing the density of gas also helps it for new stars to be born. So what we would call as proton stars. So the massive stars are actually helping smaller stars to be born. And these stars are being born inside these clouds of dust. So these are called young protostars, stars which are just about to be born. At the same time, these young protostars have their own radiation, right, which is also pushing away the gas and the dust. So what is actually happening is that these stars at some point are encouraging new starbursts, new stars to be born. But as soon as they are born, they discourage other stars from being born. And so it's got a thing what we call as stellar feedback.
And by peering at this image, because you can actually now peer through the dust, you can actually peer by looking at even longer wavelengths. You can peer through the dust. You can see these new stars being formed. So right here in the center of the image is a double star. It's a new proto-double star being formed, caused by the compression of the gas due to the radiation from the stars above. At the same time, this image gives us a wonderful image. You can see all these faint gases being formed. This is gas being evaporated from this due to the ionizing radiation. These are very deadly, how would I say, very deadly environments for people to live in, or for life to survive in. But it's the birthplace of nurseries, of stars. And one of the interesting questions is that these are very complicated processes with a lot of feedback, non-linear processes. How can we best understand them? And without the eyes of James Webb looking through the infrared, we wouldn't have been able to do this. And the best way to show this out is to give you an image of what is called as a galaxy, which is NGC 628. And this is a very far away galaxy. It's about 9 megaparsecs away. So if you think of our distance from our galaxy to Andromeda, our nearest galaxy, this would be about 7 times that distance. And this is an image of that galaxy. But what's really interesting about this image is these holes in this image. And these holes in this image are basically stars which are born and exploded and are pushing and evacuating out that gas. And you see this kind of holes, basically, it's an explosion. We always saw this in our simulation, but we never see this in practice. What you're actually seeing here between these false colors is the dust and the gas glowing in that near infrared. But what the interesting part is, that this is that same image, is that people notice that you see the big holes, but you also see smaller holes, smaller bubbles surrounding the bigger bubbles. And this is exactly the same process I told you before. It's the bigger star inducing smaller stars to be born. And they in cell explode, and then the bubbles grow in time. Stellar feedback is essential for us to understand how galaxies grow, to get to the efficiency of producing stars that they have. And James Webb is really giving us those eyes through which we can see things which we could never see before. And it's going to be an exciting time. The results are just coming out. We would spend about a couple of years, maybe a decade, just to pour through these results, because these are multivariate problems and we need to understand, not clear, simple answers. But it's an exciting time for us in this field.
Yeah, well, and very simplistically, it reminds me of those X-ray glasses we would send away for, to
Yes.
through walls, or
Yes.
but it's literally seeing through the dust.
Seeing through the dust. Yes, yeah.
That's wonderful. Well, thank you so much for this explanation of what's happening and what JWST is showing us in the early about our early universe and in the great big galaxies. After this, we'll have a short break, and then we'll talk to Brother Guy Consolmagno about more localized. So why don't we take, it's 56 where I am. So why don't we come back at 5 after, and everyone can go get a quick break, and then we'll reconnect at 05 in whatever your time zone is.
Thank you, Libby. Thank you. Sorry I went overtime.
Oh, you're great. That was amazing.
Yes.
Thank you again, Libby. Thank you again, Richard, for the beautiful images and the exploration of those through your great scientific insight. Libby said we'll gather back at 5 after.
So today we're moving from the very big stars and galaxies to talk about the planets that form around the stars. And you've described a devotion to scientific research. You've said studying creation is a way of worshiping the creator. And Teilhard had a really similar understanding. He said, may the universe offer to us, to our gaze, the symbols and forms of all harmony and beauty. I must search and I must find. And often when we look up at the stars or deep into space, I'm sure we all do, that we're brought into this state of awe. And I think it's a natural extension then to continue that searching, which for us is through a devotion to science. So my first question for you is, what is JWST searching for and finding surrounding young stars?
Well, it's interesting because as Richard pointed out, JWST was devised to look and answer the kinds of questions that galactic astronomers were interested in. But even as it was being designed, the planetary people said, wait a minute, we can actually find something about planets and address that second question that Richard asked, which is, are we alone? Because for reasons I'll bring out here, this telescope is ideally designed to look at not only our solar system, but solar systems around other stars. So just again, to give you a sense of how big the mirror is, this wall is on the wall of the SETI Institute, and SETI stands for the Search for Extraterrestrial Intelligence. And if you look carefully, you can see chairs in front of a mock-up of one of the hexo things that make up the mirror. So you get an idea of just how big that mirror is. And of course, as Richard pointed out, light comes in a variety of wavelengths. The human eye can only see a very, very narrow bit of that wavelength. And the wavelength is measured in microns, especially when we're talking about the infrared. So what do we mean by a micron? It's 1/1,000,000th of a meter. This is a human hair. And in the scale, you can see 10 microns. If I were to blow that up, that 10 micron piece would have to be as wide as what's measured to the left, so that the wavelength of light that we're seeing in visible light is really tiny, even compared to the size of a human hair. And even the infrared light is small compared to the size of a human hair, but measurable. And this wavelength has another really interesting property. You see, most things will radiate energy. Richard talked about this. The peak wavelength at which they radiate is determined by the temperature at which they radiate. So that when you look at the surface of the sun, its peak is right around where visible light is. So 10,000 degrees, these temperatures are all in Fahrenheit. You're going to be radiating at half of a micron. Now, a light bulb, which we all know from taking pictures, if you don't adjust your camera, they look kind of, give everything kind of a yellowish, reddish glow. That's because actually their peak is beyond the physical brightness. The glow of something like a molten gold at 2,000 degrees, though it's still giving off light that you can see in the visible, the peak is now well into the infrared at around 1 to 2 microns of radiation. Fighter exhaust is maybe, around 3. The kind of thing that you would see, the glowing red of the burner on your stove, the red you think of is hot. Well, in fact, it's actually emitting most of its energy well into the infrared. And it's just because it's so hot that we can see some of it into the visible. Now, when you get to about 80 degrees, as I say, a summer day in Michigan, the temperature is around 10 microns. And when you're looking at a Michigan night, it's maybe 11 or 12 microns of the peak radiation. The asteroids are actually giving off light at around 20 to 25 microns. And the objects that exist out beyond the planets, out beyond planet Neptune, what are called the trans-Neptunian objects, the Kuiper Belt objects. Both asteroids and these trans-Neptunian objects are some of the smallest bits of our solar system. They're very hard to see from inside the solar system, but there's a whole lot of them. So it turns out these are going to be some of the easiest things to see orbiting other stars. And yet they give off most of their light in the infrared. And that's why having a telescope that works in the infrared is so important. We already saw a version of this in the previous, in Richard's previous talk, where there are the camera that gives us these marvelous images has different sets of filters so that you can look into the stuff to the left of the gray bar is the short wavelength, and the things from 1 to the end, 1 to 0.5, that would be visible light. There are each individual filters that you can then translate the bandpass of each of those filters into a color to allow us to have what we might call a false color. But it's not false in that it's not stuff that's not there. It's merely a poem. We say that the colors we're assigning to the different wavelengths in the James Webb Telescope are metaphors for the colors that are actually being brought out, just as we use a metaphor in a poem to make visible the things that otherwise we wouldn't be able to understand. So these colors are metaphorical colors for the colors that we see in the telescope. And this idea of having individual bands, individual colors, also exists in that other camera, the mid-infrared camera. What does that mean to be able to look at objects with this Webb telescope? Well, here's an image made by the Voyager spacecraft back in 1986, in the visible, of planet Uranus. Relatively featureless. And you'd say, that's a pretty good image. And when I show you the Webb picture, the picture of Uranus itself, you're going to say, oh, it's not much better. Except this was the one snapshot we were able to get about 40 years ago that we've not been able to go back and see Uranus again. Not only that, what you can just barely see or really don't see in this image are collections of small bodies orbiting Uranus in rings, which are emitting light in the infrared. And the Voyager spacecraft could only see light that was being reflected off the surface, sunlight. When we go to see what Uranus looks like in the Webb, you can see not only the rings, which jump out at you, but also you can see the difference between that bright region, one different color in this metaphorical color, at the pole. Uranus is a very odd planet because it's tipped over on its side with the one pole and then another pole pointing at us. And then you have these different rings. These are particles that were dark and absorbing sunlight, invisible light, very hard to see with the Voyager cameras, but now we can see them emitting their light in the infrared. Not only can we see them, but we can also see a number of the different moons. And there are several major moons and lots of tinier moons. Now that we have the Webb, we can go back and see how has this planet changed in the 45 years since Voyager was able to see it. This ability to look at planets and to go back and look at planets that spacecraft only give us a one-shot view of is one of the major things we can do, because we can see weather. We can see whether or not there's changes in the weather as the sun goes through its various changes. How much of climate change on Earth is due to human beings and how much is due to changes in the sun? Well, we can see what the sun is doing to Uranus and say, okay, that's all we can blame the sun on. We're going to have to look at other things to recognize the climate change we're having on Earth. It's not the only outer planet we've been able to observe. Because these planets are far from the sun, they're very cold. That means that they emit light, radiate light in the infrared, in the wavelengths that Hubble and that the Webb telescope can observe. One of the interesting things about Neptune, in a lot of ways, people thought Neptune and Uranus were very much alike, except that one was tilted over. Well, Neptune is originally thought to have only arcs of rings. Now in this image, you can see that the rings are actually complete. It's just some bits are thicker than others. We knew that Neptune had a really, really bright big moon called Triton, comparable to Titan orbiting Saturn, comparable to the biggest moons around Jupiter, even comparable in size to planet Mercury. But along with that, we can now see a number of the smaller moons that, though, the spacecraft had discovered. We can see where they are now. We can see how they have evolved in their orbits, and we can actually begin to map out the gravity of Neptune by seeing, the way that these motions of these moons are different from you might have expected if you just assumed that Neptune was of just point mass. But also look at Neptune itself. You can see details going on the cloud tops of the clouds, some parts emitting more infrared light than others. And this is evidence that there's actually weather going on, that the way that heat is being carried out of Neptune is actually different from the way it is in Uranus. And we kind of knew this, but now we can measure it in more detail and come up with different models for what's going on and test them against what we actually see. I think this image of Jupiter probably gives us the best sense of what we can do when we look in the wavelengths of the infrared. An important point that both Richard and I sort of took for granted, and maybe I should mention, the wavelengths that the Webb is looking at, the infrared wavelengths, are absorbed by the Earth's atmosphere. We cannot see these from telescopes on the ground. You have to get above the Earth's atmosphere in order to be actually able to see these colors. So there was no way we could get an image like this except for a telescope designed to work in the infrared, designed to work above the Earth's atmosphere. You'll notice a couple of things in the wavelengths and the colors that the astronomers have chosen to assign to different filters. At the north and the south, there's this region that's emitting in a color that we're going to call red or orange. Those are the auroras. Just as maybe lately you've been lucky enough to see some of the auroras from the activity of the sun, we can see the sun also creating auroras on Jupiter, because Jupiter has a magnetic field that in its origins and in its shape, it's a whole lot stronger than Earth's field, but it may have an origin and being made deep in its interior, a giant magnetic field, which is causing particles from the solar wind to hit the top and bottom, the north and south poles of Jupiter. We can see different layers emitting in different colors, which tells you something about the altitude of the clouds. Some clouds are colder, some clouds are warmer. The way that this has been set up, the brighter clouds here tend to be the higher clouds. And you can tell that because there's the great red spot. Well, it's not red. It could have been assigned that color if you wanted to, but it was more interesting to assign it the color that shows that it was of a colder atmosphere. And you can take these infrared measurements and compare them against the visual measurements made by the Juno spacecraft that's in orbit around Jupiter, and come up with a much more detailed model of not just what are the clouds in Jupiter, but how do they behave? What is the physics behind them? Why is it that there's a red spot that's been around for at least 400 years? And what is the physics behind what's going on there? What does that tell us about the fluid mechanics of atmospheres that maybe we can apply to understanding the atmosphere here on Earth? So it's interesting because it's an interesting question all in and of itself, but it also causes you to step back and say, what does this tell us about who we are? Now, here's an interesting contrast. On the left, you've got this Mars image based from the satellites that have given us really detailed images of Mars. And on the right, you've got the James Webb Space Telescope image of Mars. And you say, well, gee, what's the point? What good is that? The images we got from the spacecraft are so much better, and we're getting them all the time. The difference is that we can see it in the infrared. We can see the heat, the warm spots, the cool spots, and we can do something more than just get these images in the infrared. We can then take the spectrometer and move away from the imaging mode and actually look into the measurements that allow us to see which molecules are present in the Martian atmosphere. The interesting thing about molecules is that they give off, when they're emitting light, they give off light in certain wavelengths. When they're absorbing light, they cause a dip in those wavelengths. We don't see that in our own atmosphere. The Earth, unless you're in a really, really terrible storm or something, the Earth's atmosphere is transparent. But that's not the case in the infrared. This is where different molecules absorb. Now, the Earth is trying to emit at 5 to 10 microns with a wing coming down to 1 to 2 microns. And you can see that carbon monoxide blocks most of the brightness of that light. You can see these bands of carbon monoxide. You can see the bands of water. That's why we talk about there being, carbon monoxide stopping the heat from radiating away until the Earth gets warmer and warmer enough that it can go to some of these spots in between. But this is telling us that we can see water and carbon monoxide and carbon dioxide in the atmosphere of Mars. We've got the actual data. We can fit it to a model. From this model, we can tell you not just that it's there, but how much is there, how it changes with time. One of the interesting things about Mars is it's slightly tilted. So part of its year, the northern hemisphere gets hit by sunlight and it's summer in the northern hemisphere. The other time of the year, it's the southern hemisphere that gets hit by the sunlight. It's summer in the southern hemisphere. And the pole caps of Mars are made of frozen carbon dioxide. When it's summer and that carbon dioxide goes straight from the solid sublimes into gaseous carbon dioxide, it sets up winds that stir up dust that create changes in what we can see on the surface of Mars. And these sorts of measurements give us a better measurement of how much material is there, what's going on in the atmosphere. Why is that exciting? Because we can do exactly the same thing when we look at planets around other stars. Water, we think, is necessary for life as we know it. And it's interesting that you see water vapor in the atmosphere of Mars. It's still possible that there might be or might have been life deep under the crust of Mars in the regions where water is still liquid. But now we're looking at an exoplanet. It's a hot gas giant, which means it's bright enough that the Webb can actually make out the individual spectra with a lot of error, with a lot of noise. But we see there, it is now not absorbing, but emitting, because it's hot, in exactly the bands where water emits. We can find planets around other stars that contain water that in another case, contain not only water, but carbon monoxide and methane. These are close to the materials that we might be able to then ask, are these, the productions of living creatures? Probably not on this planet, because this planet is very hot. How do I know this planet is very hot? Notice how the curve goes up until it peaks at around 2 microns. That was the temperature of boiling gold. So the atmosphere of this planet is at about 2000 degrees Fahrenheit. So no, there's probably not going to be creatures in this atmosphere. The rain, if there is any rain, is probably silicon coming out, and you can see silicates. Nonetheless, this tells you that in the future, as we apply this kind of this telescope to looking at other planetary systems, there is a chance that we might be able to see evidence of life. What would be evidence of life? What is life? What is a sign of life? To me, as a planetary scientist and a chemist, I can say life is a local violation of chemical equilibrium. We breathe out carbon dioxide, but there are plants there that turn the carbon dioxide back into oxygen again, which is a violation of chemical equilibrium. It's got to get energy from some place to reverse the entropy. And it does that from sunlight hitting the leaves of the plants. Carbon dioxide, carbon monoxide, you would expect that to be in equilibrium. It's curious that you have carbon monoxide and methane, but there will be an equilibrium balance. if I can find a planet where there are materials that are wildly out of the equilibrium you'd expect, for instance, free oxygen, as you might see in ozone, then you might get really excited that, I don't know if there's life there, but at least there's a violation of chemical equilibrium going on. So this is why the Webb telescope can give us new answers or allow us to at least ask new questions about, is it possible that there could be places outside of Earth where there might be life? There's one last story that I want to tell, and but before I get there, let's take a break here. I think this is probably a good resting place rather than, I was going to do it a couple of slides ahead, but I think this may be a good starting point. So Libby, go ahead and I'll turn it over to you for a minute.
Great, thank you. It's so clear that JWST is helping us learn so much more about the planets, their moons, what orbits around them, the same, their atmospheric composition. And I think that it's really neat what that tells us more about Earth, as you said, helping us to differentiate humanity's impact on Earth as opposed to what might be naturally occurring or what we could see from the sun. And that's so important in this time. It makes me think about the power of awareness, which is really possible through our consciousness. And Teilhard was fascinated by humanity's consciousness. He said, no longer merely to know, but to know that one knows. Admittedly, the animal knows, but it cannot know that it knows, in a very Rumsfeldian sort of sentence. You've written about the power of imagination in a little book called My Theology, which I totally love. And you said, to quote you, how you encounter God with the same tools that you use to encounter the universe, your senses, your reason, your imagination. And I just think that the connectedness there between consciousness and awareness with, our hopes, our imagination, our dreaming, as you described, the colors are metaphorical. It's a beautiful poetic way of considering our coloring of these images. Scientists explore what we can see, sense, we apply reason and logic, but really we dream or imagine what might be or why it might be. There's
If I can, push even further on that.
Yeah.
It's very easy to be the kind of materialist that believes only in the things I can see and touch. But here we are looking at a universe in wavelengths we cannot see, and looking at things we cannot touch, and yet they are absolutely real. The universe is bigger than what we experience day to day walking around with, worrying about where's the refrigerator and where's my next meal. And that, I think, is one of the great messages of astronomy. It reminds us of a universe that is so big, the incredible distances that Richard was talking about, and so rich, and so full of unexpected and yet very real. And that's why I go back to an image like this, or image where people say, oh, those are false colors. Well, they're not false colors, they're metaphorical colors. If I was to write a love poem and say, love is like a locomotive, so it doesn't mean that when I'm falling in love, there's this, train going to show up. But rather, only with these metaphors can I communicate a truth which is very true. And these metaphorical colors are telling us truths which are very true, and which we have created instruments to allow the things we can sense with, namely our eyes, to see the things that otherwise we could not see.
Well, and I think too, it's a translation, right? Like we're translating these images into our limited visible spectrum. What visible is only what is visible to us. So taking these images and translating the nitrogen spectrum and the oxygen spectrum, even in those figures that you showed, to a way it's relatable and understandable to us.
And in a way that we can comprehend all of it all at once.
Yeah.
Somebody in one of the comments earlier talked about images rather than numbers. Well, I love numbers, and there are times when you have to get down into the numbers to really understand what's going on. But you want to see the numbers in a context. And these images give us the context in which we are human beings and creatures of this same glorious universe.
Oh yeah. Well, and I love that you say that, you know, the images that we're finding, the data that we're finding, we often think of these as answering questions, but the way that you said it is that it's allowing us to ask new questions. And I that's so hopeful and future focused, which is so Teilhardian. I'm wondering, what is it that JWST scientists are hoping or imagining they might find? You've got my interest piqued with your upcoming story.
Well, I'll start with this dark cloud. And we heard from Richard how stars are formed in dark clouds. He's interested in the stars. He's one of these stellar astronomers. Stars to me are only interesting because they give me a place for planets to form. And it's the planets that I'm interested in. One of the fascinating things about this image is what are we looking at here? This is a region where a star is being formed, but let's take a closer look at that star itself. You'll notice the dark region. Basically, from 50 years ago when I was a student and we had ideas of how stars and planets are formed, you have a collapse, a compression of gas and dust. The dust will block the light. And if there is any kind of spin to this, the top and the bottom can collapse because there's no centrifugal force stopping it from collapsing. But everything in the disk, parallel, perpendicular to the spin axis, that is going to be where the dust is compressed into a disk. So we're looking in this particular image deep into the disk where the light is being blocked. And in fact, light from the protostar would like to be shining in every direction, but the disk stops it from shining to the left and to the right. And so the cloud that is still there is not lit up because the dust stops the light from getting there. Let's talk about that dust. We saw that the human hair was way, way bigger than 10 microns. Even flower dust is about 30 or 40 microns across. Cigarette ash, however, will be at around 10 microns. Wildfire smoke particles can be down to about 1 or 2 microns. Here's the reason why that's important. If the thing you're shining light on is bigger than the wavelength of light, then the light might be absorbed by it, or it might be reflected by it, but it's not going to get past it. But if the thing you're shining the light on is smaller than the wavelength of the light can sneak by, might get scattered a little bit, but you'll be able to see it. That's why looking in the infrared allows us to look through dust clouds, but only if the dust is really small or the wavelength we're looking at is really big. So, if stars were covered by human hairs or wheat flour, you probably still wouldn't be able to see them in the infrared. But if the stars are covered with dust, the way that dust is accreted or condensed from a very hot cloud of gas, the tiny particles of dust, that's exactly the kind of dust that would block visible light, but allow infrared light to go through. So the fact that we can see this difference tells us not only we can see through the dust, but it tells us something about the dust itself. And these are, to steal a picture from what Richard was showing us. From the left, we've got a star formation region. From the right, we can actually look at the stars, and even better, some of the disks where the stars are being formed. Now I'm going to take a step back, go back to the way that I was taught planetary science 50 years ago, because we knew how stars were formed from a cloud of gas and dust. If you have a cloud and the cloud is cold enough, the gravity will compress the dust. The more material you have, the more gravity you have. The heat is what stops the dust cloud from collapsing, but heat doesn't scale with size. Gravity does. So if you have a big enough cloud, it will collapse, and it will collapse into a spinning ball of gas and dust. As it gets colder, you get more and more dust condensing out of the hot gas, which is turning into a cold gas. You've got light in those red lines squirting up above and below while material is still accreting onto that disk. That was pretty much the picture we had. And it turns out we see disks very much like that. So that much must be true. That's what our theories told us 50 years ago. That's what we're seeing today. Well, the other thing we knew 50 years ago was that the planets had an interesting pattern. You had small rocky planets close to the sun, and you had big ice and gas planets far away from the sun. This was clear. This was a pattern. This was telling us something. And by golly, I can explain exactly how that happens. You see, when you're close to the star, the gas is still hot enough that the only things that condense into dust will be silicates, hence rocks. Hence, you'll have small rocky bodies. But when you get just far enough away from the star, that water ice can freeze out. You've now got 3 times as much material because there's a whole lot more oxygen to make water than there is silicon to make rock. And that means that you would then have snowballs of ice and rock coagulating, getting bigger and bigger, faster and faster, so fast that they could attract the gas from the gas and dust to make the gas giant planets. And out of this, you would predict 3 things. Number 1, all the planets should be in the same plane going around the star because they're all in this nice disk. Number 2, you ought to have rocky planets close to the star and gas giant planets far away from the star. And number 3, because once you have this ice ball growing, it should immediately leap from the size of Earth, which is relatively small, to the size of Neptune, which is quite big. And there should be no planets in the size range in between. And this was so brilliant and so clear and so obvious that it was taken as a tenet of faith. Well, in the 1990s, we began to actually see planets orbiting other stars. And the first planets we saw were planets the size of Jupiter, but orbiting close to the star. I can explain that. That's just because those are the easiest ones to see. Once we finally actually see lots and lots of solar systems, we'll realize that those are just the exceptional ones. Well, we have seen lots and lots of solar systems, and not so exceptional. The other problem was that problem I was mentioning, that you ought to have gas giants at a certain size and rocky planets of a certain size and nothing in between. And in the 25 years that we've been discovering planets around other stars, what we have discovered is the vast majority of the planets we have discovered are right in that gap that my favorite theory told me was impossible. Great. What this does is to remind us that the sun is a star, but most stars are not like the sun. Our solar system is a solar system like thousands of other solar systems, but most other solar systems are not like our solar system. And this means that the Earth may be a far more unusual place than my favorite science fiction stories would have you believe. It is a new way of thinking about the universe. Not that, life is impossible elsewhere. We don't know if you need a solar system like ours to have life, because we've only got the one example of life. We can't tell. But it's the sort of thing that makes you wonder. Back in the 1990s, we actually had evidence of planets orbiting other stars. But back then, all we could do was actually see the star itself and see how its light was redshifted and blue shifted and redshifted and blue shifted as the star was jerked around by a big planet orbiting close to it. However, even in the 1980s and into the 1990s, with infrared or microwave telescopes, we could see that stars, in this case was Fomalhaut, the brightest star in the constellation of the Southern Fish. One of those bright stars you see in the southern horizon in the fall. that in fact, rather than being a particular star, it seemed to have more than one kind of lump radiating in the microwaves. Now, microwaves are out even beyond the infrared, which means that they're showing you even colder material, but also because they're longer wavelengths, you don't get the same kind of beautiful resolution. All you can see is kind of lumps, and that's the best you can do. The Herschel Space Telescope, again looking in microwaves, was able to actually see a ring of material around Fomalhaut and tiny concentrations of material that made you think maybe there were planets. Indeed, one of the telescopes here in Arizona, using adaptive optics and the Large Binocular Telescope, was able to resolve tiny dots of light in that ring that make you think we could actually see the planet itself in a disk of material going around the star. This was quite a remarkable feat. Well, since we know there's something there, one of the first things you do with the James Webb is to point it there. And now we're looking at the temperatures where this material is radiating. And not only can we see the outer ring, but we can see material inside. In fact, their black spot is merely to block out the brightness of the star itself. So what we're seeing is material that is outside of the star. And there's more than one ring of dust. That outer ring kind of reminds you of the Kuiper Belt. All of those bodies that are ice and pretty cold orbiting out beyond Neptune. But that inner ring looks like a disk of material, not necessarily a disk of material that is still forming a planet. In fact, there are characteristics that make you think rather it's the dust that came from bodies that were running into each other, grinding each other up, creating a cloud of material from planets that were not so nicely behaved, that did start running into each other as they were moving from where they were formed into closer to the star or farther away from the star. It's a solar system very different from our solar system, but it's a solar system that is a real place and reminds us that the universe is richer than we might have imagined. So I end with this sort of blow up of what we hope we can begin to see, not just that we can see disks, but we can see into the disks, to see different solar systems in different stages of their evolution, to see better. Because, if you were actually on a planet looking out, you might have a hard time seeing any of the individual bodies in these disks, but because we're far enough away, we can see them all at once. They are radiating and whole enough of the infrared light that our telescope can see the structure inside this very young solar system. I end by pointing out one last thing. If you want to know more about planets and planetary science, at our website at the Vatican Observatory, vaticanobservatory.org, we actually have a podcast. And last fall, I did a podcast with Heidi Hamel. She's the woman in charge of the planetary observations for the James Webb Telescope. It's something that she's dedicated 20 years of her life. She's also an old friend of mine. I knew her back when we were both at MIT. She was an undergraduate in the band that played for the musical theater, and she played in a production of Fiddler on the Roof, where I played the rabbi because of the beard. So it's a fascinating conversation. If you want to know more about the people who make all of this happen, I recommend take a look and see what she has to say.
Well, wow. Just wow. I think the thing that I appreciate most that you and Richard have both brought out is the images for comparison, because I don't think we realize quite how incredible the advancements are and the changes. I mean, you showed Hubble, you showed Voyager, Maxwell, Herschel, all the differences that each of these individual telescopes are showing. But yet how much more JWST can do, and in terms of asking questions and wondering. It's fascinating.
And one of the bad things is now that we've got all these new questions, we want, oh, if only we had a bigger telescope. If only we could look at this. It never ends.
Well, and one of the things that I think about, because back when I was at NASA Goddard, 2010 is when I left, they were still doing the JWST then. And at that point, they were like, it really should be up there. This has really taken a long time. But I think that says something about the hope and the hard work and the longevity of what scientists do. And what we do in this aerospace field is, this isn't a right now, tomorrow kind of thing. It's, we're looking far out into the future and recognizing that what we do takes time. And I think whether or not all scientists admit it, there's a great faith in that. There's a great faith in believing that what we're doing matters and what we're collecting matters.
It's like a giant cathedral that the people building it know they may not be around to see what it finally looks like at the end. The two cameras that Richard talked about are the principal scientists are a husband-wife team here at the University of Arizona. People who I knew when I was a student 50 years ago, George and Marcia Reiki. And George Reiki is now 80 years old. Finally, his camera is, beginning to show things.
Yeah, that's patience.
Yeah.
Andrew, I see you joined us.
Yeah, so I just want to say thank you to Brother Guy for a really mind-blowing presentation there. Paradigm shifting, I would say, especially in building after or off of Richard's presentation earlier. And at this point now, we're going to transition over to the questions that our viewers and listeners have been asking in the chat. So talking about a shift in paradigm, Angela Mano asks, where did the question go? She says, or she asks rather, are we coming, and this is prefaced by the quote, the object of science is to falsify science. So she asks, are we coming to the end of one paradigm and on the verge of a new one?
We don't know. I think Richard made that very clear in the way he presented his material. There's something interesting there. It's going to take some time to think about it. You really don't want paradigm shifts. You can't make progress if everything that you thought is pulled out from underneath you. And some philosophers of science are take the Kuhn model of a paradigm shift and say, yeah, but science isn't quite like that either. Rather, it's not that we learn that something was wrong, or even that there's more to it than we thought, but that there's more than one way of thinking about it. And that might be happening here. We don't know yet. Richard, you want to, since this is really your side.
I agree with Brother Guy. It's just too early. Oftentimes results need to be confirmed. We need to rethink. Maybe I made mistakes along the way or say things about it. It's just too early. Within a few years, we'll have the answers. We don't have to wait too long. So it's going to be within a year, these things will be confirmed or will be shown that it's not true. But also the things which have been really paradigm shifting, at least in galaxy formation, has been got through approximative techniques and weight confirmation. And once we have that confirmation, we can really start rebuilding things. But until we have that, it's just too early. It's just too early. I agree with Guy.
Yeah, and certainly in the solar system formation, there was always the awareness that this could be wrong, but it doesn't seem to be. We talked about the nice rocky inside and gaseous outside. We saw that in the solar system. You saw that also in the moons of Jupiter, Io being rocky and Callisto being icy. And you said, oh, two examples, it must work. Of course, it doesn't work at all for the other moons of the other planets. And it turns out they're more typical than Jupiter's moons. We didn't know that. And you only know that when you gather a whole lot of data and you're able to stand back and say, okay, it's like a poem. You analyze a poem by reading the entire poem, getting an idea what the poet was trying to say, and then wondering, why did he use this word instead of that one? All of a sudden, this is the phrase that catches my attention. And that's how you can, unravel and pull apart to figure out what the poet was trying to say. We do that the same way in unraveling the science.
Very good. So not a shift in paradigms, but a possible expansion of paradigms, perhaps. Great. Great. Thanks.
Somebody in the chat mentions Lakatos's work, and one of the great things I was able to do as a Jesuit, they forced me to take philosophy, and there happened to be a philosophy of science class where I learned how little I actually knew about the philosophy of science.
So we have another question here from John Fox, who asks, can the Webb telescope identify stars and other galaxies that are the size, composition, and age of our sun?
Yes, Webb is doing that at the moment. So these so galaxies which are pretty close by to us would be within 3 to so let's put it this way, within 10 megaparsecs, and within 10 megaparsecs would mean 10 times the distance to the Andromeda galaxy. We could already see that with Hubble, so that doesn't really give us much of an advantage. So we already could see stars, individual stars, and study their composition with Hubble. And is this going to be much faster with Webb? But that will Webb will take us out maybe to 14, 15 because of its bigger mirror. But it's something which we have been doing with Hubble, and we are continuing to do with Webb.
Thank you. So we have another question here that asks the idea of, as we zoom out from the planet Earth and we see our smallness amongst the grandiosity of everything, where does the role of consciousness come into play?
To me, consciousness is the reason why it exists. It's not that it's a weird accident that we happen to have conscious creatures on this one planet, but that consciousness itself, whether it is confined to planet Earth or common in the universe, is a necessary prerequisite to love. And to me, that's central to who God is and what the creation is all about. A creator who is big enough that, tiny as we are, God can still pay attention to each one of us. That's what infinite means. And I think only in such a big universe does consciousness and love and beauty have the possibility to express itself in so many ways.
Thank you, Brother Guy. Father Richard, do you care to share it all?
I really don't have much to add. I really agree with Brother Guy. I just think, like, to point out that, just our level of, it's just admirable with all this new data, and trying to make sense of it is really where our consciousness is really coming to that fore. It's only through our consciousness that we can make sense of it, make sense of our place in the universe. And I don't know whether there's other consciousness out there. It would be nice, but we don't have that proof, and we don't have that evidence yet. But it's just amazing to see how we ourselves, through our consciousness, unique among the animal kingdom, can make sense of all this information out there.
One of the former directors of the observatory, George Coyne, put it very succinctly in that in us, the universe has become self-aware and can appreciate this. And also the idea of God being infinite and able to concentrate on us is an idea I've happily stolen from another member of our community, Chris Corbally. So there are a lot of good ideas out there and well worth stealing. I'll mention in passing a book that all the good ideas came from my co-author, Paul Muller, which, let's see if I can get this. Would you baptize an extraterrestrial? And the answer is, it's a great question. We don't know the answer, but there was a comic strip when I was a child called Pogo, and very philosophical. It sort of had the wisdom of Doonesbury and the art of Bill Watterson and Calvin and Hobbes. And then the two characters are talking, and one of them muses, some people say that there are intelligent creatures out in the universe smarter than us. And other people say we're the most intelligent creatures in the universe. Either way, it's a sobering thought.
Well, I think too, what makes us so unique is that we ask the questions. You know, consciousness at its root is interest in what's around us and out there, and the ability to ask the questions and to continue to pursue and probe. That, you know, it's really in the questions that we ask that shapes the answers. And to continue to question is so important, that we should be looking, we should be considering the extraterrestrial and what is out there. And if we're lucky enough to be able to see it in our exact time when we're all living, well, that would be great.
We probably won't find it easily, but we really look foolish if we hadn't ever looked and it turned out to be there all along.
Yeah, very true.
A great question that someone actually touches on here. And as you mentioned before, I forget if it was Father Richard's or Brother Guy's presentation, but you're talking about how we can see things that we can see, right, with our visible light spectrum, and then the modifications and augmentations that we can make to that. You know, that would imply that we're talking about visitors from outer space. And there's so many theories, like Jacques Vallée has an interdimensional hypothesis when it comes to extraterrestrial life. But to get back to this question here from one of our participants, David asks, what are the implications for soteriology of the discovery of extraterrestrial life?
I'm going to leave that to Richard. He's studied more philosophy than me, so he knows what that word means.
So theology, sociology, salvation. I mean, theology basically is the study of salvation, the study of human salvation, the study of Jesus as a redeemer. And this raises an interesting question: if there is intelligent life out there, does Jesus come to redeem all humanity, or all intelligent life, all forms of life, or only humanity? And how does he get that message to them? So those are all questions. I'm happy that I'm an astronomer and don't have to deal with these questions, because these are really complicated questions that could get me in trouble with the church, just like here. But I'd like to point out that coming from India, I think some of these questions were raised 400, 500 years ago when, you know, the church met people in the New World. Didn't know that they were humans, that. But it's this mixing of culture, this encounter of cultures. If we ever do meet an extraterrestrial life and discover life, it would be an interesting encounter of cultures if we can communicate in some ways. I'm happy I don't have to deal with that question. It's above my pay grade.
It's also a question that people were thinking about thousands of years ago, because, you know, not only do we have the Greek legends of, you know, other monsters and other creatures, there's nothing unusual to them, that these are the people that Jason and the Argonauts ran into. But even in our own tradition of angels, we have creations of God who are in a relationship with God that is very different, and whose choices are very different, and the choices they were forced to make very different from what human beings have. So ours isn't necessarily the only model of salvation. But I think any creature that's free to choose right and wrong is going to have to deal with the reality that sometimes you make the wrong choice, and therefore need salvation.
Yeah, and if we follow the Jesuit maxim of God in all things, well, how far do we take all things, right? In Teilhardian sense, all in all. So maybe one final question here that hits home for perhaps the two of you is, how do Jesuit astronomers perceive God or the divine? And how do you worship, as Teilhard might ask?
To me, the important thing is, just as I do all of this study of astronomy, and then I walk outside and look at the stars overhead, and I realize those are the same things that I've been studying. There's not one astronomy that's in my computer and another star that's in my eyeballs looking overhead. Likewise, the creator of the universe that I experience in the love and the joy and the beauty is the same thing as God encountered in the person of Jesus Christ. And that means that no one picture is adequate to do justice to what we're seeing.
I think I've robbed this maxim which Libby quoted earlier from Brother Guy itself. I
And
heard
who
it
knows
from
where
him
I
many
stole it
years
from?
ago.
Who knows where I stole it
So
from?
the more we study the universe, the more we begin to understand the God who created it. What I really enjoy about science, and I think this is typical about Jesuit science, is to reach out to places, is reaching to the frontiers, right? Jesuit mission is about reaching to the frontiers. Science has always been a frontier for the Society of Jesus, for the Jesuit order, and partly because of this reason of beginning to understand this marvelous creation which God created. And studying science as we try is all about breaking paradigms that we've been talking about. And our own faith journeys is all about God breaking us and making us, into on our faith journeys. And I think I see these parallels typically in my life. Most of my days are quite sad and delusional because all my lovely theories and all my lovely work is not coming to fruition, and I have to change my ideas. And I think the similar thing is being asked of me in my faith life, to break out from my older patterns of, you could call them sin, and to reach out to newer patterns which Christ and Jesus is offering us, patterns of life, of relationship, of reaching out to our brothers and sisters in new ways. So there are a lot of parallels, and I think it's I wouldn't like to call it a uniquely Jesuit way of doing science and worshiping God, but I think it's a gift which Saint Ignatius has given us and is available to all the church, and many people have made it their own over the last centuries.
And of course, the genius of Teilhard was that he saw in the new and rapid developments of science of the last century this tremendous opportunity to see and encounter the same God of Scripture in ways that we wouldn't even have known we could have encountered him.
Well, and I think what I like so much about the way that Teilhard encounters God too is it is through the earth. It really helps us to have this earth-rooted spirituality, or cosmic, really, spirituality. But it's through the work. He was so focused on work. One of my favorite quotes of his is, God is at the tip of my pen, my spade, my brush, my needle, of my heart and of my thought. That God is integrated in everything, all aspects of work. And that is such a Jesuit maxim.
Why do we do the work? Ultimately, what is it? Is it for the pat in the head, or make a living? At the end of the day, the science we do is so difficult and so tedious at times that you have to have that sense of God at the end of it. And God expressed through joy of discovery, through beauty of seeing how the universe works, and through the love that it inspires in us of creation and the Creator.
Very well said. Guy, Richard, Libby, thank you so much for your insights today, for sharing your very well put together and obviously a lot of time went into those presentations and your comments and all that you've had to offer, and really expand our sense of the cosmic here. So thank you so much.
Thanks for inviting us.
Absolutely. Now we'll turn it back over to Sister Kathy.
Thank you, Andrew. And thank you, Father Richard, Brother Guy, and Sister Libby for such an integrated look at our world. And thank you, Sister Kathleen, also for the beautiful poem that you read. I'm sure we have all learned so much about our amazing cosmos. But more than that, we've been filled with wonder and awe. Thanks to all who have joined us today, and to all who will watch this program on YouTube. We hope you will continue to attend our programs. If you're not already a member of the American Teilhard Association, I invite you to join. But before leaving, we have a real treat for you. Sam Guarnaccia and John Cimino have composed 2 new songs for this occasion to honor the wisdom of Pierre Teilhard de Chardin. So although we are already filled with the beauty and wonder of the cosmos, we allow the beauty of the words and music of these songs to open us to a hope-filled future and impel us toward the fire of love.
We are one, after all, you and I. Together we suffer. Together we exist. And forever we'll recreate each other. Driven by the forces of love, the fragments of the world seek each other so that the world may come into being. The history of the living world can be summarized as the elaboration of ever more perfect eyes within a cosmos in which there is always something more to be seen. The world has caught fire in my sight until a flame all around me. It has become wholly luminous from within. Such has been my experience in contact with Earth. At the heart of a universe on fire. The universe is growing luminous like the horizon just before sunrise, causing a ferment of art and science thought. Let us open our arms and hearts and look at the immense crowds all over the world. Build and seek to welcome the waters, the flood, the sap of humanity all over all that we love, all that we hope, all that we dream. Let us call down the fire. The most profound way of describing the evolution of the universe would be to trace the evolution of love. Love alone is capable of uniting living beings by what is deepest in themselves and draws together the elements of the world. Moving ever upward toward greater consciousness and greater love. At the summit, you will find yourselves united with all those who, from every direction, have made the ascent. Love, the threshold of another universe.